Okay, so I hope you can see this. So yesterday, I gave an introduction of cosmic ray observations, and we started talking about cosmic ray transport equations. And let me briefly remind you where we ended up yesterday. We were looking at the evolution of the cosmic ray phase-space density. So phase-space density was defined as number per particle of particles per phase space volume, which is spanned by dx, dy, dz. So the space volume element, the infinitesimal space volume element, and dpx, dpy, dpz, which is the stream momentum. And Liouville's theorem tells us this very simple equation that the total time derivative is equal to 0. And if we express the phase-space density in terms of its canonical variable, the location and the momentum, then we arrive at the Blastoff equation, which is just another form of expressing the Liouville's equation. So the last step that I did yesterday was to look for configurations where I not only have a regular constant magnetic field that would basically give us a simple solution of gyrating cosmic rays around magnetic field lines. We talked about that. But on top of this regular component, I also introduced now a turbulent component, a random component. So if we are looking for a volume average of cosmic rays, then this random component should average out. It should be equal to 0. And in statistical physics, we can replace this volume average also as the ensemble average of magnetic field configuration. So these bracket notation that are indicated here in green down below, this is basically the ensemble average now, where I basically consider all possible turbulent magnetic field configuration. And we can, in this configuration, when we're looking for the evolution of the phase-space density, I can now decompose the phase-space density F in terms of a component that is corresponding to the ensemble average. And I use this new notation here, which is basically this bar. So F bar means the phase-space density in the ensemble average. And this has a small correction, which is delta F. And this is basically the difference between F and F bar. And I can do the same also for the Lorentz force. The Lorentz force is given by the contribution of the background magnetic field, which is called FA bar. So it depends on B bar, the regular magnetic field, or B0. And we have a random component that is going to average out in the ensemble average. This is this part. And the equation that we derived this way was the following. So you take the Blastoff equation, this equation here, and look for the ensemble average by replacing the phase-space density and the Lorentz force via this expansion, and using the fact that delta F and delta FA individually vanish in the ensemble average, we end up with this ensemble average Blastoff equation, which basically looks like the original equation. So this part here on the left-hand side, but now on the right-hand side, we don't have 0. We actually have a term which is the ensemble average of the small correction of the Lorentz force, depending on the turbulence, times the momentum derivative of delta F, which is the correction of the phase-space density. So we can now do the following. So this was how we ended up yesterday. So today we are looking at the difference between the Blastoff equation and the ensemble averaged Blastoff equation. So this here is the Blastoff equation, and this here is the ensemble average Blastoff equation. And by looking for the difference, we can now derive a differential equation for the small correction delta F. And this looks as follows. So I will not go through the details here. I will just present you the final expression. So delta F now has also the time derivative here, and then the gradient multiplying the velocity, delta F. And then delta F is following the gyration with respect to the, sorry, this is not Let me correct this. So this is F bar. And we have to sum here over index A, delta F. And then on the right-hand side of this equation, we have a term that goes like minus delta FA. So this is the random Lorentz force, which is multiplying the momentum derivative of the average component F bar. And then we also have here higher order terms, which are scaling like the square of these perturbations. So the first term here that I showed you, that is linear in these perturbations introduced by the magnetic field. But we also have here two more terms, which are square terms in terms of delta F and also delta F. So this is the Lorentz force, and this is the phase-space density. And these two terms are going to be neglected in the following. So this is going to be an approximate equation. Now, if you look at this equation, you again see that here on the right-hand side, we basically have the original Blastoff equation, but now the Lorentz force is replaced by the ensemble averaged Lorentz force, FA. So we can actually write this left-hand side of the equation as a total derivative of this correction delta F, which is depending on time. And I can express this in terms of R bar and P bar. Yeah, so this is here identical to this expression. So what means R bar and P bar? So R bar and P bar is basically the gyro motion of an unperturbed particle. So this is the solution to location and velocity that I talked about yesterday when I was looking for the simple gyration of cosmic rays along magnetic field line. Yeah, so and realizing that this is identical to this expression now allows us to find a very simple solution to delta F. And for that, I have to switch back here, make a new page. Yeah, so we can now find a solution to delta F, which looks as follows. So so delta F at times t, and here for the sake of brevity, I am omitting now the dependence on location and momentum. So this is basically implied by this expression. So this is given by delta F at some time in the past, and for simplicity, I just assume that this is extending to minus infinity. And then I have here an integral, which is taking into account the right-hand side of this expression here, which is the integral over dt prime from minus infinity to t. And then I have to evaluate the term on the right-hand side, which was the random Lorentz force times the momentum derivative of the regular component. So this term here is now evaluated along the path RT prime. So RT prime, R bar T prime, that is basically the gyro motion of a particle along the magnetic field line, unperturbed by any magnetic turbulence. So this is a path R bar, and this is the regular background field that I denoted B bar. So, so this is a correction now to delta F based on our ensemble average quantities. Now, from the discussion last time, we have already introduced the collision term. So the collision term dF over dt was given as the ensemble average of minus delta FA and then momentum derivative of delta F. So this was the collision term. And now I can use this approximation here, which is also called quasi-linear approximation, and derive an expression of this collision term where we now only have the ensemble averaged phase space density of the cosmic rays and the magnetic turbulence, which is encoded by delta FA, the corrections of the Lorentz force. And this expression looks as follows. It's again the ensemble average, and then I have delta FA, the derivative, and now I have to include this time integral from -infinity to t dt prime, and I evaluate the path along the regular component, and this is the path r t prime, and then I close the ensemble average. So this is now our master equation, how we can find an approximation for the collision term, taking into account the presence of magnetic fields. Are there any questions at this moment? Okay, good. So this, you can imagine that this expression here is quite complicated, and it's not possible to solve it exactly. In quasi-linear theory, you can find a solution, but of course, it's nevertheless an approximation of the collision term. So what we are going to do in the following is we will approximate the collision term in the following way. We will write this as a term that goes like minus nu, and then we have here the ensemble averaged phase space distribution minus phi, and this expression phi here is going to be the angular average of the ensemble averaged phase space distribution. So it's a double average. So it goes like 1 over 4 pi, the integral over the momentum direction, p hat. So hat always means a unit vector. And then I have here the ensemble averaged phase space distribution f hat. So this, this approximation here is basically introducing a damping term. So we expect that the presence of magnetic turbulence will in time average out the distribution of momentum and space distribution of our phase space distribution via repeated collisions. So this is our expectation. And so this relaxation of the phase space distribution to a completely smooth ensemble average distribution, this will happen on a time scale which is determined by the collision rate, and the rate of collisions, this is this factor nu that I introduce here to scale this contribution. So if I start from a configuration which is not the angular average of the ensemble average phase space distribution, I expect that in time I will approximate a phase space distribution that is very smooth. So this is the motivation to abbreviate this term by this expression here. So we can, if you look at the expression here from quasi-linear theory, you see that you're basically forming the ensemble average of magnetic field configuration at different locations. So this delta FA is basically the ensemble, the magnetic turbulence at time equal 0. And delta FB is integrated along this gyro radius. So it's basically probing different regions in space and different magnetic field configurations. So in the following, we will make a qualitative discussion of this expression. So qualitatively, first of all, we are going to look for a very simple type of turbulence. We are looking for isotropic turbulence. So there is no preferred direction in the occurrence of turbulence. And in this case, we can parameterize the level of turbulence by looking for the 2-point correlation function of the turbulence. And this 2-point correlation function of turbulence is most easily expressed in terms of Fourier space. So if we introduce here delta B tilde as the Fourier transformed expression, so delta BA is going to be 1 over 2 pi to the power 3. And then the volume integral here weighted by this exponential factor, which is multiplying the location with k. Then this is going to be the original space configuration of turbulence. And this is the Fourier expression here on the left-hand side. So, and for this expression, the isotropic turbulence is going to have an ensemble average that looks as follows. So the ensemble average of delta B A, depending on the vector k, and delta BB, depending on the vector k prime. This is going to be a function that has only contribution if k and k prime are identical. And then it's scaling with the function gk. And then it is multiplied by a tensor that looks as follows: delta AB minus Ka, Kb over K prime plus I sigma K epsilon ABC Kc over K. Yeah. So this is the most general expression for the 2-point correlation function in Fourier space for isotropic magnetic turbulence. So there's no additional orientation introduced by this correlation function. And this additional tensor that appears here at the end, this is basically taking care that the dispersion of the magnetic field is equal to 0. And so we are introducing here two functions, one function gk and one function sigma k. So these are two real valued functions. And the function that is going to be important for us in the following is actually this first one, g of k, because this is the one that is actually related to the power density of the magnetic turbulence. So we can look for the energy density of the magnetic turbulence. So the energy density of magnetic turbulence is given as the ensemble average of delta B squared divided by 2. This is because we are working with heaviside Lorentz units. So if you were working in Gauss units, this would be delta B squared divided by 8 pi. So there would be an extra factor 4 pi. So this is the expression in heaviside Lorentz units. And if we are now using the definition of the magnetic field, the magnetic turbulence in terms of 2-point correlation functions in Fourier space, we can simply write this expression as the integral over dk. So k is going to be the total length of the Fourier mode k. And then we have k squared g of k. Sorry, this is a bit sloppy here. So this is supposed to be a g. So you see that if this is the total energy density of the magnetic turbulence, then we can now define the power of magnetic turbulence as pk equal to k squared times gk. So so this is basically, so the power distribution of magnetic turbulence depending on different Fourier modes. This is going to be the characteristic that is going to drive cosmic ray scattering in magnetic turbulence. And typically what one assumes for isotropic turbulence in cosmic ray diffusion is so-called Kolmogorov turbulence. So in the case of Kolmogorov turbulence, if you look at the distribution of power in terms of different Fourier modes, you have a power law that is bounded to the left by k min. So k min is going to be 2 pi divided by some large length scale. So this is typically called the outer scale in turbulence. And it will be bounded below by a maximum Fourier mode, which is related to the inner scale, so the minimal length scale. And the rest of the power is basically then distributed following a power law along this line. So this is here pk. And well, it's logarithmic units, so that's the reason why I can draw actually a straight line there. So I should say this is here the log of pk, and this is the log of k. And yeah, so integrating this entire distribution is going to give back the magnetic field, the energy density of the turbulence. Now, if we go back to the definition here of the collision term, this definition here, we see now that basically as the particle is gyrating around the background magnetic field, it will probe the magnetic turbulence at different location. And if we translate this now back into Fourier space, it means that it will try to scatter with the individual energy densities of this magnetic turbulence, depending on the trajectory of the cosmic ray gyrating in the background magnetic field. So the picture that you should have in mind at this point is the following. Let's say that we have here a patch of space, and we have some regular magnetic field component, which for the sake of simplicity, let's assume it's pointing into our direction. So we have here a magnetic field component pointing in our direction. And so a particle is, of course, now going to make a regular motion in this background field. Yeah, so this is going to be here the gyro radius with a certain Lama radius. So this is the configuration where we simply ignore the magnetic field. But now on top of that, I have now magnetic turbulence. And this turbulence will appear at different length scales. So basically, if I look at my magnetic turbulence and if I average out certain if I average out over certain volume elements in these magnetic field configuration, I will emphasize different strength of the magnetic turbulence level. So, for example, if I'm looking for a certain Fourier mode, yeah, I will make clear in a second what this is all about here. So these are basically here regions in space where the random component has different direction, completely uncorrelated directions. And the distance between these different orientation, these patches in the sky, the distance will basically be 2 pi divided by the Fourier mode of the corresponding turbulence. And now you can see if you have a particle that has a Lama radius, which is of the order of the average correlation distance of these magnetic turbulences, it will receive quite a strong contribution from the appearance of these turbulence along its path. If I, for example, would consider a configuration, which I indicated here in yellow, a configuration that has a very small Lama radius, something like this here, then this Lama radius will not really experience different orientation of the magnetic turbulence on this corresponding distance scales corresponding to 2 pi divided by the Fourier mode k. If on the other hand, I have a very large Lama radius, indicated like this, I will on the other hand average over many, many different field configuration, and this contribution will effectively average out. So the bottom line here is that as a cosmic ray with a certain gyro radius is orbiting, is performing a gyro motion along the magnetic field line, it will most strongly interact with those Fourier modes where the Lama radius corresponds to 2 pi divided by k. So if I go back here on the right-hand side in the power spectrum, I can basically indicate the corresponding Fourier mode, which I call here the resonant Fourier mode. And this is given by 2 pi divided by the Lama radius. So this will be the part of the spectrum where I would expect that cosmic rays have the strongest contribution in terms of this washout effects coming from the magnetic turbulence. This is the picture that you should have in mind. And so this very qualitative picture, of course, you can go through the calculation and you will find that your integral can be approximated by a delta function that singles out the corresponding resonance modes in the power spectrum. But this is a qualitative understanding of how this is happening in terms of physics. And so now we can make, based on this argument, we can now make an estimate on the size of this scattering term. Yeah, so we can now make the following estimate. So the scattering rate nu that I introduced for this approximation here on the right-hand side, this is going to, well, it's going to be 1 over length scale in natural units because it's 1 over time. And I can approximate this as, well, the length scale which is given by our problem, which is basically the Lama radius. So this should go like 1 over RL. And then it should be proportional to the relative energy density of my turbulence compared to the overall energy density of the magnetic field configuration. And because I only look here for the resonant interaction, I basically have to single out the contribution along this power law. And this is going to be approximately the power law pk times k. Yeah, so if I have a logarithmic distribution and if I want to find out what is the contribution of this power law distribution at a certain point in space, then this is the first estimate that I multiply this distribution by the Fourier mode itself. And this is then divided by the total energy density of the magnetic field. So yeah, so this is of course not telling us what the prefactors are of this expression, but this is how we can approximate the rigidity scaling of these scattering terms. So we have already introduced the Lama radius. So the Lama radius was depending, is linear with the rigidity of cosmic ray. So this is this capital R. And now for the turbulence, I assume that this turbulence is following a power law that goes like k to the power minus alpha. And for example, in the case of Kolmogorov turbulence that I mentioned earlier, alpha would be equal to 11/3. And so if I now look for this expression here, k times pk, this is going to scale as k to the power minus alpha plus 1. And so in terms of Kolmogorov turbulence, this will go like k to the power minus 5/3. Is that correct? No, this is not correct. This is, sorry, this, so this is actually, so G, I'm sorry, I have to make a correction here. So for Kolmogorov turbulence, we have to assume that this expression here, so this GK, this is scaling as k to the power minus 11/3. But the power itself has an additional factor k squared. So the alpha that I have here is going to be 5/3 and not 11/3. My mistake. So this alpha here, let me correct this. So this alpha here is going to be 5/3. And so now if I look for minus alpha plus 1, this is going to be minus 2/3. Minus 2/3. Minus 2/3. And but now the k that I'm singling out in my power law, this is actually 2 pi divided by the Lama radius. And the Lama radius itself was proportional to the rigidity of the particle. So that means that if I take into account the first factor, 1 over RL, and the Lama radius dependence of this factor here, I end up with a rigidity dependence that goes like R to the power minus 1/3. So this is minus 2/3 coming from this factor, and plus 1 coming from the prefactor of this expression here. Yeah. So in the following, we can assume that in this approximation here, where we approximate this complicated looking term in terms of a simple damping term in terms of the angular distribution of cosmic rays, we can assume that this rigidity, the rigidity dependence of this term will go like rigidity to the power minus 1/3. Okay. So are there any questions at this point? Okay. Then, so this is now our basic expression or modification of the Blastoff equation, replacing this collision term by this effective term that scales with nu. To make some further progress, we have to make a further expansion of the Blastoff equation in terms of spherical harmonics, and I've already talked about this briefly yesterday. And for simplicity, we will only look for the first 2 terms of the spherical harmonic expansion. So spherical harmonic expansion of the ensemble average Blastoff equation. And here we will have the monopole term, which is the term that I've already introduced when I was talking about this effective collision term. And we will also have here the so-called dipole term that is going to be given by this expression. So again, if I have a vector with a hatted notation, it means that this is a unit vector. So this is basically the average of the ensemble averaged phase-space distribution projected onto the direction of the momentum of the velocity vector. So if I now go back and use this expansion in terms of the Blastoff equation, I can basically write down a sequence of differential equation for different orders of the expansion. And for us, only the first 2 terms will be important. The first term is given by the time derivative of the monopole So this is here the monopole, and this is here the dipole. And this will scale as the velocity b. And then you have here the gradient of the dipole, and this is equal to 0. So this will be the first term. Then the second term of this equation will be then the time derivative of the dipole. And this has now three different contributions: beta over 3, the gradient of the monopole contribution, and then a term which is scaling with the Lorentz force of the regular background magnetic field. And I can use our notation in terms of this omega vector. So we introduced P dot equal to P cross omega. So I'm using now this notation of omega for the Lorentz force. And this is going to be epsilon A B C. So the Levi-Civita tensor, omega B, and then the dipole C. And then here on the right-hand side, I will have a contribution from this collision term that is scaling with the dipole. So these are the two master equations now. And if we are now finally look for the so-called diffusion approximation of this expression, we will make the following two assumptions. So the first assumption is that the time derivative of the dipole component is going to be close to 0. So that means the configuration, the angular configuration of the phase space density will be, in terms of the dipole distribution, will always be close to the steady state solution, whereas the monomole contribution can have a strong time dependence. So I will still assume that the time derivative of the monopole here is not equal to 0. But by using this diffusion approximation, I basically look now for the steady state solution of this expression here. And so for the steady state solution, I will also introduce a tensor, which I'm going to write in the following way. So I will introduce this tensor in terms of its inverse, k to the power -1, AB. And for reasons that will become apparent in a second, I will define this with this prefactor 3 over beta squared. And then I have here the collision term, nu delta AB, minus epsilon ABC, ABC omega C. So this term here is basically coming from this expression. This term here is coming from this expression. So I can combine these two terms that appear in this expression and write down a steady state solution to the second equation. And so the second equation now becomes the gradient, the gradient of the monopole is going to be minus k to the power -1 AB. And then I have here the projection onto the dipole phi b times the velocity beta. Yeah, so this is now the expression of equation 2, and we can solve this expression. We can now write phi a is equal to -1 over beta, and then we have k ab times the gradient of the monopole contribution. So this gives us a relation between the dipole of the phase space distribution and the gradient of the monopole via the tensor k that I introduced here. And this is actually the inverse of the diffusion tensor. And this is, so because of this inversion here, I introduced this tensor as an inverse itself. Okay. And so finally, at the end of the day, we can now use this steady state solution of the gradient, sorry, the dipole in terms of the gradient of the monopole, and insert this back into equation 1. So this was the time derivative, the time evolution of the monopole. And this will give us finally an expression, which is delta t phi equal to the spatial derivative with respect to RA. And then I have here the contraction with the diffusion tensor, and then a second derivative with respect to B acting on the monopole contribution itself. Yeah, and so this is a very famous equation. This is the diffusion equation. And K here is the diffusion tensor. Now you can actually write down, I'm not going through the details here, you can write down the explicit form of this diffusion tensor. And in general, the diffusion tensor will have 3 contributions. And these contributions are parameterized in terms of 3 different scattering rates. So we have beta square over 3 nu parallel, which is projected onto the orientation of the background magnetic field. Then I have a contribution which is orthogonal to this, delta AB minus omega A, omega B hat. And we have an off diagonal contribution as well, an asymmetric term here that scales like epsilon A, B, C, and then the direction of the background magnetic field. And these 3 quantities here, they can be expressed in terms of our original scattering rate. So nu parallel is simply going to be identical to nu that we introduced earlier. The perpendicular scattering rate is given by nu parallel, so the original scattering rate plus the gyro frequency squared divided by the scattering rate. And this contribution here will be identical to the gyro frequency plus nu parallel squared over the gyro frequency. So this simply comes out after you go through the exercise of inverting this matrix K that I introduced as the inverse of K. And the final expression then gives you this orientation along magnetic field axis with characteristic scattering rates. Okay, yeah, so this is basically a very essential equation, which is called the diffusion equation. And now, so basically the picture that we have in mind now is the motion of a cosmic ray particle will be scattered by the appearance of turbulence. And so this is here a simulation where this turbulence is taken into account by a random Brownian motion of cosmic rays. And for this Brownian motion of cosmic ray, you can estimate that the typical distance a particle will scatter is depending on the square root of the numbers of scatters, so the square root of numbers of deflection in turbulent magnetic fields, times a typical length scale, and this is the effective diffusion length scale that we have to find out here. So I think this is now a good time for a break where you can ask some questions.
Sorry, can I ask, yeah, I have, in the previous slide, what is the letter in the subscript in the last term? I don't read.
So you mean this letter here?
Yeah.
yeah, so I introduced here new parallel. So this is the sign of parallel, new perp, and new A. And new A means basically asymmetric diffusion, or it's also sometimes called drift diffusion. Yeah, yeah. So basically, maybe it's easier to look at K in a specific axis. So if I assume that the magnetic field orientation is proportional to the z-axis, then I can write this diffusion tensor in the following way. I have here on the diagonal axis the beta squared over 3 mu perp, beta squared over over 3 nu perp, and beta squared over 3 nu parallel. And these entries will be equal to 0. And then I have this asymmetric contribution that goes like b squared over 3 nu a and minus beta squared over 3 nu a. So the different signs here are coming from the Levi-Civita tensor here. So this will be the expression of the diffusion tensor if the magnetic field is in the z direction. This expression here is a more general form where I can use arbitrary magnetic field directions. Okay?
Yes, thanks.
Any other questions right now? Okay, then let me, we can always talk about this later once you have digested. And again, today I will also post the lecture slides and you can have a look and try to find out what I was writing down here on my iPad. So let us now look a little closer here. What is actually the absolute? So this is here the relative scaling of the length scale. So n here is the number of scatterers. So this should increase linearly in time. So I would expect that the distance of a cosmic ray traversed after a certain time is going to be proportional like this to the square root of the time. So we can also do this a little more quantitatively. We can look at the diffusion equation again. My handwriting is slowly degenerating here. So the diffusion equation. So let me write it down again like this here. I can write this as plus. So this is another vector form of writing the diffusion equation. And then here on the right-hand side, I previously had 0, but of course, if I look for cosmic ray emission from sources, I also expect that this expression has a source term, and the source term is typically expressed by a quantity that is called Q for Quelle in German, yeah, source. And this will depend on time in general, location, and also the so it's not the absolute P, it's going to be the absolute scale of the momentum, because we are looking here at the angular averaged phase-space distribution. So these quantities will all depend on the absolute value of the momentum, but not on the vector itself. So this equation can be solved for arbitrary configuration of source distributions, and so it's useful to give you the Green's function. No, Green's function. Green's function of this expression. So the Green's function is going to be the solution in the following form. I have the time derivative of a function g that depends on t and r, and also by 2 parameters ts and rs. So S here stands for source. And so this is going to be, this is going to be the definition of the, let me give you here the result already. So the Green's function of this expression is given by 1 over 4 pi delta t to the power 3/2, and then 1 over the square root of the determinant of the diffusion tensor k. And then I have this exponential term here that is basically a Gaussian dr transposed k dr divided by 4 times delta t. So these are here vectors dr. So dr is defined as r minus rs, and dt is defined as time t minus ts. So this is the Green's function of this differential equation, which means that it's a solution to the following expression, dtg plus the gradient of k, so divergence of k gradient phi is equal to delta t minus ts delta r minus rs, and then I have a function qp here, which is going to be the emission spectrum of a source. So this could be like a power law distribution, as we will find out later. So this is the solution of this equation here. And if we, for example, now look for a simple setup where I say I have a source which is located at rs equals 0, and the source is given an impulse of cosmic rays at times ts equal 0. And if I also assume isotropic diffusion, meaning that the diffusion tensor KAB can be approximated as the isotropic diffusion scale times the identity matrix delta AB, then I can write down the solution to the expression, the angular averaged phase space density, the monopole, via this equation. So this is going to be integrating over rs and time ts, and then we have here the Green's function and the initial configuration, which now becomes simply qp delta ts delta rs, because it's all at the origin. And this expression has a simple solution. And if in the case where we are only looking for isotropic diffusion, this is simply 1 divided by 4 pi times then the scale of the diffusion tensor to the power 3/2. And then I have here this Gaussian behavior minus r squared divided by 4 time and the isotropic diffusion scale. Okay, so this is of course a simple Gaussian distribution. So a Gaussian distribution in 3 dimensions. So this has the general form 1 over 2 pi sigma squared to the power 3/2 e to the power minus r squared over 2 sigma squared. And now if I compare this to the solution of this diffusion problem, I can identify that sigma square here is identical to 2 times the isotropic diffusion scale times the time of after the emission, the time lag after the emission. And if we can now look for the average location, so the average r squared of a Gaussian distribution, and you might remember from one of your courses that this is going to be 3 times the variance of the 3-dimensional Gaussian, so 3 times sigma squared. And so this is now going to be 6 times the isotropic diffusion scale times time. So that means the average distance that a particle traverses in a time t in isotropic diffusion is going to be 6 times the isotropic scale times the time lag. And this is basically now the quantitative form of this previous expression that I wrote, like the square root of n times lambda. So this is here now showing you that this expression here is scaling as the square root of the time due to this Brownian motion of cosmic rays in the magnetic turbulence. Okay, are there any questions on this?
Sorry, I have a question. In the previous slide.
Previous slide?
The green function is the solution of that equation, but why so in the solution does not appear essentially a part that depends on the momenta, if is it present the right hand side?
Right. So first of all, I see here now that this should be a G. Yeah, so this is here G. So basically the left-hand side of the diffusion equation that appears here only depends on time derivatives and the divergence and the gradient, right? So this is independent on momentum, and I can basically derive solutions for fixed momentum. That is the reason why we do not have to worry about momentum here. So the Green's function will simply have a term that is proportional to an arbitrary function that represents the spectrum of cosmic rays emitted at the source. Keep in mind that the phi that we have here, that was coming at the end of this rather lengthy derivation of the ensemble average space days distribution, which then on top of it is also averaged with respect to the spherical harmonics. So phi is basically is averaged over all cosmic ray arrival direction. Yeah. So the only dependence which is left after averaging out the arrival direction of cosmic rays is only the dependence on the overall scale of the momentum of the particles. And this is indicated by this P.
Okay, yeah, yes. So in the expression for G should appear the Q factor or not?
Oh, yes. Oh, I'm sorry. Yes, you're absolutely right. You mean in this expression here? Right.
Okay.
You're absolutely right. Sorry, I misunderstood your question.
No.
So this should basically scale as QP here, right?
Okay. And so in the final integration does not appear Q. Otherwise,
yes. So if I write it like this here, then I do not have to include this term here. If on the other hand, I choose to define the Green's function here without this factor, then I have to enter this in this expression. Yeah. So you're right. So the way that I've defined it here, there should not be like this. So there should not be any contribution here. Yeah.
Okay.
Yeah. Thank you for checking that. I guess to be more precise, a Green's function in a mathematical sense would be defined without this Q factor here at the end. So then this expression where you had a 1 there would be the one that would be the solution of this expression, and then you would have to include the Q factor in the final expression of phi. But it doesn't really matter here where we introduce this Q factor. Okay, thank you, Davide, for this correction. Okay, then, let me try to connect back now to cosmic ray physics. So we will see later on that you can measure this diffusion tensor, or at the diffusion scale, by the observation of cosmic rays at Earth. And the diffusion scale can be approximated in the following form. So the isotropic diffusion scale will depend on the rigidity of the particle, and this is coming from the dependence on the scattering parameter nu that I introduced on the rigidity scale. So this diffusion tensor will have the size in our galactic magnetic field environment, which is of the order of 10 to the power 28 centimeters squared over second. And the rigidity scaling will go like 1/3 if we are considering Kolmogorov turbulence. You can also consider other types of turbulence where you have a different type of spectral index or rigidity dependence in your diffusion tensor. But just as an example, let's consider Kolmogorov turbulence. And this prefactor here, 10 to the power 28, corresponds to a rigidity scale of the order of gigavolts. Yeah, keep in mind, rigidity was defined as momentum divided by charge. So the unit of rigidity is in terms of volts. And yeah, so if we now, for example, consider cosmic ray diffusion over length scales of the order of maybe 1 kiloparsec. So let's assume that the average diffusion length is of the order of 1 kiloparsec. So our distance from the galactic center is of the order of 7 to 8 kiloparsec. So 1 kiloparsec is about the size of the length scale of the galaxy. And inverting this equation now that we derived here, we can now estimate a time scale that it takes for cosmic rays at 1 gigavolt rigidity to arrive at Earth. So this will simply be 1 kiloparsec squared divided by 6 times the isotropic diffusion scale. And this will be of the order of 5 mega years. Yeah. So this is the time scale for cosmic ray diffusion at this rigidity scale across our galaxy. So this is an enormously long time scale. The light travel time at 1 kiloparsec is about 3,000 years. So this factor here is a factor of 1,000 slower than the light travel distance between a source at 1 kiloparsec that I observe in light and the cosmic rays that eventually arrives at our location. Now, if there are no further questions at the moment, I will add one more ingredient which is important for the diffusion of cosmic rays, and that is convection. So instead of looking for the random motion of cosmic rays as they are interacting with magnetic turbulence in the galactic magnetic field, there can also be convective motion, so bulk motion of cosmic rays. And so this bulk motion of cosmic rays can be introduced by going back to the original Blastoff equation. So this looked as follows. So we had PA over P0 F and FA. Yeah, so this was before we made any approximation in terms of turbulence and phase-space distributions. So we can now make a coordinate transformation, which is accounting for bulk motion of cosmic rays. So we are basically making the following substitution. We leave the time identical to the original time and also the location. But now the velocity let me actually write the Blastoff equation here in terms of the velocity term, which is VA. So the velocity is going to be the velocity V star. But now I will add a second term to this, which is going to be a new velocity, U, which depends also on location. Yeah, so it's basically a velocity field that can depend on location. And in general, this will parameterize the bulk motion of cosmic rays, whereas V star is going to be the random motion of cosmic rays that are encountering magnetic turbulence. So I can now, using this substitution, we can now define a new phase-space distribution. And this new phase-space distribution is called F star, and it will depend on the new variables T star, R star, and P star. And it is defined by the original phase-space distribution, which was a solution to this equation here, but for the shifted coordinates. So this is T star, R star, and then here I have P star, which has to be corrected for this bulk motion term, which is minus m gamma. So this is P0 in natural units times the velocity that I introduced. And this will then again depend on R star. So now if I'm looking for the transformed Blastoff equation, so the Blastoff equation for the transformed quantity F star, I can write this as in the following form. So the time derivative, so the time definition has not changed. So the first term is going to be identical to the original term. Then the second term has to be corrected for the new definition of our velocity VA. So this is VA star plus U A multiplying the gradient. And this is also going to stay the same because the definition of location has not changed, F star. But then I also have here in this equation a dependence on the location in the momentum term of the original equation. So that means if I now look at the gradient of this expression, I have to add a second term, which is now VA star plus UA. And here I have now the derivative of the new phase-space distribution F star with respect to the new coordinate RA star, acting on the definition of the new momentum, which has this explicit dependence on location. So the second term here can be written in the following form: P B star over RA star. And now I have here the derivative with respect to P B star. And then here the final term is again the Lorentz term, which is just FA. And then here I replace this by the start quantity. So this is now going to be the transformed Blastoff equation, where we took into account the bulk motion of cosmic rays. And so you see that there is one term here that is going like the derivative of the new momenta with respect to RA. So this term here is going to be PB star RA star, and this is given as minus m gamma And now here you have the divergence, or rather the gradient at this point of the velocity field with respect to location. Yeah. So this term here is basically also depending on the background velocity. Typically, this bulk motion is non-relativistic. So at least we are treating this as a non-relativistic bulk motion in the following. So this term has a dependence on u. And since I have here a second term depending on u, this is actually here a higher order correction that scales like u squared. So the background velocity squared. Utendo, do you have a question? If you have a question and if you have you're experiencing feedback via Zoom, you can also write the question in the chat, and I will answer this question. So the first term that appears in this term here is scaling like u squared. So I can for the first order approximation drop this this dependence here on UA, and we are basically left with two additional terms to the Blastoff equation. And these two additional terms go like this here and this here. So the two terms are the convection term with respect to the flow. And we have here one correction factor that is written as PA star. And then you have this derivative here of the background bulk motion. Sorry, my handwriting is terrible. B RA star, which is multiplying the momentum derivative of the new phase space density. Yeah, so this term here is also known as the convection term. Now this is here the so these are the two new terms that we find after this substitution in variables in our Blastoff equation. Now we can go through the same exercise as we did before, and of course we are not going to do this in great detail. We are looking for the collision term. We are expanding the ensemble average in terms of spherical harmonics, and we are looking then for the monopole and the dipole. And so taking into account all this algebra, we will end up with a term of the monopole contribution of this new phase space distribution F star that is going to look like this here, UA. So the convection term will not change. And now I have here phi star, which is the monopole of the phase space distribution. And then as a second term, I will have this momentum integral, which is coming from the averaging process when I expand in terms of spherical harmonics. And this will go as PA star, PB star. And then I have here the derivative UB delta RA star 1 over P star P star. So the monopole only depends on the size, so the absolute value of a momentum and not the momentum vector itself. And so this averaging here, will basically give us 1/3 delta AB. And so that means this final expression here can be expressed as 1/3 of the gradient of the velocity times P star times the derivative of the monopole with respect to momentum. And of course, the first term is just UA A star phi star. So these two terms are now introduced in our revised transport equation of the cosmic ray monopole. And of course, here we have to add also the original terms. So I have here the time derivative of phi star, which is adding onto this convection term. And we also have here one contribution, which is parametrizing the diffusion term. So this is all expressed in terms of start quantities. But of course, at this point, we can also drop this notation. And this is equal to 0 here on the right-hand side. So this is now the general diffusion equation of the angular averaged phase space distribution that we are going to use in the following. So we have here the time derivative, we have convection, we have diffusion, and this term here, that is actually in the form of an energy loss term. So you have here a derivative with respect to momentum, and this energy loss term is proportional to the gradient, the divergence of the magnetic field. So this is also called the adiabatic energy loss term, which is simply coming from the space dependence of the velocity field that cosmic rays are following on top of diffusion. Now, yes.
In the previous slide, the Lorentz factor gamma, is it with respect to V star, with respect to which velocity?
No, so here, so you see in the original equation, let me try to indicate this in red. So we had here VA. So this is PA over P0, and P0 here is defined as M equal gamma. Yeah, so this is basically the factor that comes in here. Yeah, and this factor M gamma is then in the second step, once you look for the derivative factor here, combining together with the velocity to form momentum again. So M gamma times VA is identical to PA star.
Okay, so it is VA therefore.
So in the original Blastoff equation, you have VA. VA can be expressed as momentum divided by the energy in natural units. And so this factor M gamma is equal to so M gamma is equal to the energy of the cosmic ray, which is here multiplying the velocity vector, simply using this expression here. Yeah, so here this transformation is in terms of V. So if you want to write down this expression here in terms of the 3 momentum, you have to multiply this expression by M gamma, and this gives you this additional factor M gamma multiplying the bulk velocity. Okay.
So basically, now in order to understand, so the gamma is 1 over the square root of 1 minus a velocity squared in natural units.
Exactly.
So my question is, what is that velocity? It's not clear.
So basically the bulk velocity is, so I parameterize the velocity of the particle in terms of its random motion which is driven by the magnetic turbulence on top of the bulk motion of cosmic rays. So if you imagine that if you have a source, and we have actually the one exercise that Johan was introducing today, where you look for the solar potential, we're looking for cosmic ray diffusion in the background of plasma, which is emitted from the sun. So this will introduce a bulk motion, radial motion from the sun. And so this is a way to account for this bulk motion by looking for this variable substitution in this way.
All right, thank you. Yes.
Yeah. So naively, if you have if you had just a constant motion that doesn't depend on location, you would only modify the Blastoff equation by having one convection term. So this is probably the simplest case. But now there are various situations in astrophysics, and we will encounter one situation when we are looking for diffusive shock acceleration, where the velocity is actually strongly depending on location. And so in preparation of what we are going to talk about tomorrow, cosmic ray acceleration, we have to introduce this additional adiabatic loss term, which accounts for the gradient of the velocity field. Okay, so this is here now our final master equation of the evolution of the monopole of the phase-space distribution. Of course, similar to what I talked about in the case of this diffusion example, I can also add now source terms to the right-hand side of this equation. You can also imagine that cosmic rays are not only interacting with magnetic fields, they will also interact with other particles, they will also interact with gas and radiation. So all these additional interactions that cosmic rays have will lead to additional terms in this expression. So this expression, which is shown here, is simply giving you the evolution of the phase-space density, just accounting for diffusion, convection, and adiabatic energy losses from the gradient or the divergence of the the bulk velocity of the plasma. Yesterday, I also introduced a quantity which I called the spectral density. So the spectral density, so the spectral density was defined as, so it was denoted by this quantity small n. And in terms of the angular averaged phase-space density, this simply is 4 pi divided by beta times p squared times phi. So phi was the angular averaged phase-space density. So multiplying this by 4 pi p squared basically gives you the total number of particles that share the momentum with absolute value p. And by dividing this by the velocity vector, you convert the flux of these particles in terms of a density. So the quantity here on the left-hand side has a dimension of number of particles per volume and per energy. So this is basically how many particles of a certain momentum do I have in a box of a certain size. And so it is useful to express this expression here, this differential equation of phi star in terms of this spectral density. And for that I have to look at this term here. So this term, sorry. So we have to look closely at this term that I indicate here in red. So after dropping the start notation, I can write this as P del phi over del P. And if I now use the definition of the spectral energy density, this is going to be 1 over P squared beta over 4 pi. So I'm not going to go through all the details of this derivation, but you can convince yourself that this is identical to this expression. So now I have expressed this momentum derivative of the phase-space distribution by two terms here that depend on n. And I can combine this together with the original equation. So we had also the term that scales like the so the convection term that scales with the bulk motion, this term here. And I combine these two quantities in the following way. I have beta over 4 pi, 1 over p squared, ua del ra n. So this is simply replacing phi by n using the definition of n. And then I have these two terms which are coming from the above equation, which I can write as the gradient of u times n minus 1/3 of the gradient of u. Sorry, I always say gradient, it's the divergence of u. And then I have here the momentum derivative of Pn. And these two expressions here in front, they can simply be written as the total divergence of u times n. So the final expression, which I really only abbreviated here for the interest of time, is going to have the following form. So now I have a differential equation in terms of the spectral density, time derivative with respect to n. And then I have here the convection term, which now takes the form of the gradient of u times, the divergence of u times the spectral density. And I have here the adiabatic loss term, again scaling with the divergence of u. And then the time, the momentum derivative of p times n. And I have here finally the diffusion term, KAB. Yeah, so this expression here is completely equivalent to the previous expression, which I expressed in terms of the angular averaged phase space density, but using this definition, which converts the phase space density in terms of the local cosmic ray density, which can then be directly related to experimental measures, can be expressed in terms of this expression here. And this is indeed the expression that I also provided in the, or that Johan provided in the exercise today when we are talking about the solar potential. Okay, I think I have something like 2 minutes left. Is that right, Darius?
Yes, right.
Yeah. So maybe in the last 2 minutes, I can maybe also say a few words. Yeah, maybe let me close on that. So we have focused on the monobore contribution. So the total angular averaged contribution. But we have along the way in deriving this expression, we have also used the diffusion approximation, and we could show that to first order, the dipole is actually proportional to the gradient of the monopole projected onto the diffusion tensor divided by the velocity beta. Yeah, so that means even though cosmic ray diffusion in magnetic field will isotropize the distribution by random scattering, there's a small residual anisotropy in the arrival direction of cosmic rays, phi a. And so cosmic ray observatories with a very good statistics, so collecting a lot of data to allow to infer very small differences in the arrival direction of cosmic rays. They are looking for these small anisotropy, and this is indicated here in this plot. So this is here an intensity plot of cosmic rays with an energy of the order of 10 tera electron volt, or corresponding to a rigidity of 10 teravolt. And these are observations taken by Tibet in the northern hemisphere and by IceCube in the southern hemisphere. And what you see here is the relative intensity. So you see basically similar to what you maybe are familiar with the cosmic microwave background, you're looking for excesses and deficits in terms of the average expected arrival of cosmic rays across the sky. So this is the difference with respect to the monopole contribution. And you see that there are actually very interesting large-scale features in the sky, like a large bluish deficit region, which has a size of the order of 1 per mil. So this here goes down to 0.002 in relative intensity. So that means if I look in this direction, every 1,000, so 1 out of 1,000 cosmic rays arriving from this direction will have a preference to not come from this direction, but rather from the opposite direction, which is indicated in red. This is, I think, the way to put it. So the anisotropies that cosmic ray observatories see, they are quite complex. In this diffusive approximation, we are focusing on the dipole, and the dipole has an orientation and a strength. And this is here a summary of the dipole anisotropy coming from various experiments. Here in the lower plot, you see the total amplitude of the dipole. And here in the upper plot, you see the orientation with respect to the equatorial plane. And you see that there are some very interesting things going on in dipole anisotropy. You have a very strong dependence on energy. And in particular, when you look here for the orientation of the dipole, which is proportional to the gradient of cosmic rays, there seems to be a flip of orientation at an energy of the order of 100 tera electron volt. So below, it's rather stable, coming from a direction of, let's say, 40 degrees, and then it makes a flip, and it's basically pointing to a direction which is consistent with the location of the galactic center. So I can say maybe a little bit more tomorrow on this very interesting observation, but I think for today, I've run out of time. So thank you for your attention.
So are there any questions? We have more or less 10 minutes for questions.
Yes, in the previous slide, is the difference in the size of the two colored blobs a feature of the coordinate system?
Yes, there is a dependence on coordinate system here. And the reason for that is kind of involved. So the thing is, these measurements, they are all taken by cosmic ray observatories which are sitting on the ground. Yeah, so these are these ground-based observations that are able to collect a large amount of data over time. And basically, these observatories have not the possibility to point in a certain direction. The pointing of these observatories is basically done by the rotation of the Earth. So over the course of 24 hours, the ground-based array is basically scanning the sky, and then after 24 hours, the scanning repeats. And then if you collect the data over a long period of time, then you can collect your cosmic ray data into individual bins and try to analyze anisotropies. So for example, the Tibet array, as the name suggests, this is sitting in the Tibetan mountains at, I think, of the order of 45 degrees latitude north. And this is the reason why over the course of 24 hours, this is the field of view of this observatory. So the coordinate system, so coming back to your original question, is basically always with respect to the equatorial coordinate system, simply coming from the rotation of the Earth. And there's and also because of the fixed observation of cosmic ray observatories, these observatories are not capable to decipher cosmic ray anisotropies which are scaling in the vertical directions. So these ground-based observatories can decipher cosmic ray anisotropies very well on the horizontal direction, but not in the vertical direction. And this is the reason why in this colored plot here, you see when you, as you approach the northern pole and the southern pole, you go back to color green, which is basically saying that there is no anisotropy, but this is mostly an observational effect. So if you want to interpret these anisotropies in the arrival direction, I mean, I could give like a 1-week lecture on this if you ask me too much. Then it's very important that you also take into account observational limitations to interpret the data.
I see. Thanks.